talk about the real numbers today. A new episode on sets of numbers, and this is for now the last one in this first series. It's basically concluded. All that's going to come after that are just some practice sessions on distributive laws, associativity, etc. such that you get a lot of practice, okay, for exams, for example. So real numbers, there's actually not much I would like to say about them. Actually, there's a lot I would love to say about them, but we don't have the time for that, and most high schoolers don't have the knowledge for that. So we are just going to talk about the most important thing that R is going to give us, namely that we can do everything in R, and also that we can act continuously on R. R is continuous. It means we can draw lines, okay, without stopping at each and every finite point. I'm going to talk about what this means in a second. At first, let us discuss what R actually is yet again. So R is basically the set that includes all the rational numbers, but also all the irrational numbers. For example, in R, we have that there is square root of 2. I said it at the beginning, or we have transcendental numbers. All transcendentals are also irrational. For example, E or pi. Really doesn't matter, okay? Those are the most famous boys. There are other boys like the omega constant, for example. We don't know if the Euler-Mascheroni constant is indeed irrational. I believe it is, but this doesn't matter right now, all right? So how can we put this into kind of set notation? I mean, like I said before, the reals are just the rationals together with the irrationals. We haven't defined this set before because it's kind of hard to define the set of irrational numbers, all right? But just take it as a given. It's just what we know up until this point times together with the irrationals. A set of numbers which are quite curious, okay? They are out there, they are pretty mysterious, but they help us go from discrete to continuous. Let me elaborate. So on the real numbers, just first things first, everything works. Subtraction, division, addition, etc. Associativity, distributivity works. The reals are yet again a field, meaning it's boring because everything works nicely there. Now, most algebraists really don't like any fields because they are really boring. They rather deal with semigroups and shit like this just because it's really more intense, and there are way more restrictions on those numbers. So yeah, never mind. So reals, you can do everything, but they are also continuous. What this means is, imagine the natural numbers at first. Natural numbers, there are infinitely many of them, but what you can do is start at the lowest natural number, for example 0 or 1, and then you can count up 0, 1, 2, 3, 4, 5, etc. So you can count them starting from the lowest. Same spiel with Z. I know there's no smallest negative number, okay? That's not something there is, but we can basically count them yet again. It's kind of obvious that you can count them. I mean, you can go -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, blah, blah, blah. Same with the rational numbers. You can choose a really big denominator, makes the whole fraction small overall, and then you can just start counting yet again. 1 1,000th, 2 1,000th, and so on. You can basically count those fractions yet again. There are infinitely many of those, but there are way less infinitely many rational numbers than there are infinitely many real numbers. Not going to go into detail about this, just take it here. Q, N, and Z are countable. You can count them basically. Reals are uncountable. You can't count them anymore. I mean, where do you even want to start? For example, a nice example, it's basically the main question where analysis stems from is, what is the lowest positive number? What is the smallest possible positive number? I mean, does this even make any sense? I mean, I could go to the blackboard and say, well, obviously the smallest possible positive number is 0.001. And then John from behind could come here. Come here, John, could you come here? All right. Hello, my name is John. He could come here to the blackboard and say, well, obviously I can put a 0 more here, and this makes it smaller. I mean, Yeah, obviously, that thing is smaller than this one. And now Samantha, for example, Samantha, could you please come? No, I don't have any Samantha here in this room, okay? We're only male individuals here. So Samantha could basically come here and say, well, I'm going to put 1,000 zeros here, and it's going to be smaller than both of those. Now the next one could come, and so on. So that's a real question. Is there possibly a smallest positive real number? No, there isn't. And this is what analysis is all about. For analysis proofs, when dealing with continuity, limits, etc., we always define ourselves some epsilon greater than 0. It's some real number greater than 0, but it's also not the smallest one. But it's so small that it could go arbitrarily close to any positive real number, okay, in some kind of neighborhood, in a little ball around it. So we can close into any real number, doesn't matter how small it is, and we could come arbitrarily close. And this is where the topic analysis all just comes from, okay? We assume stuff like this, and then suddenly everything works out, continuity and stuff like this. So here's one lesson you need to learn. You can get arbitrarily close to any real number. You can actually approximate those with fractions, but you can't really get to any real number which is the smallest one, okay? It just doesn't work. And this is the same with any real number. We can approximate any real number, for example square root of 2, really nicely using fractions, but sometimes we just can't get to those, except there are some values like square root of 2. So on Q, you can imagine it like this. We have some kind of number line, okay? And you could put fractions here, for example 0, and we have 1, and we have 2 here. But the thing is, we are going to put little dots here. For example, we have 1/2, then we have 1/3, really doesn't matter. And then in between you could squeeze another fraction, which is like half of those two. And then between 1/3 and this half you could put another fraction, etc. But doesn't matter how many fractions you put in there, one after another, there's always going to be a small gap between those rational numbers. You can never make this line really closed. All those rational numbers are going to be a small thing, a small number apart from each other. It's kind of curious, right? I mean, we could put infinitely many here, but it really won't work to get ourselves a closed line. And this is where real numbers are for. Okay, what real numbers are for? For example, between 1 and 2, there's square root of 2. It's like 1.4 something. So it's kind of here, okay? So this is square root of 2. Now we could say, I mean, 3/2 is close to square root of 2, and then maybe to the left there's something that is really close, okay? Really doesn't quite matter. And now we could zoom in a bit more onto square root of 2, and then we could go even closer to square root of 2 with another fraction. But the thing is, square root of 2 can't be expressed as a fraction. It's an irrational number. It is not rational. So square root of 2 is never equal to some a over b, meaning it's never a fraction, meaning it's not in Q, it's element of the rational numbers. So meaning, no matter how close we get to square root of 2, we can never express it with some element out of the set of the rational numbers. Just doesn't work out, all right? But we can approximate it arbitrarily close, and there are infinitely many of those irrational transcendental numbers here. So many there are that we can actually close this line to a closed line. So we can connect all the points here on this number line, and we can close it up. This thing is now not discrete anymore. It doesn't have any small gaps between numbers anymore. It's a continuous line. It just goes through. And here, we are going to make use of that later. For example, just put another axis here, okay? Then you have an x-axis here and a y-axis. And instead of just going by the rational numbers on this line, if you would just go by the rational numbers, you could just go like this, for example, on the curve, because, well, you would need to leave gaps between those rational numbers, okay, between those pairs of points, pairs of coordinates. But now with the real numbers, this thing can actually be closed, okay, to a line which goes continuously through. And yeah, this is what real numbers are for. It just helps us make things way nicer, okay? We can keep stuff continuous. We don't need to act discrete anymore. And this is everything I wanted to say about the real numbers. They are just there. I'm terribly sorry. They are just there, but they are extremely helpful. And this is like the biggest set you are going to deal with in your school life later in the game. I hope you enjoyed this video. If you did, please like, subscribe, recommend channel if you like. Whew, this already concludes this series. I tried my best. I hope it wasn't too bad. Okay, I'm going to get used to all of this over time, but just give me a few videos up until I can get everything scripted out and reduce pretty nicely to high school stuff. This was already pretty advanced here, so with this epsilon neighborhood stuff. But yeah, this is just what the reals are, alright? Can't do anything about it. I'm seeing you in the next video. Watch the video to its fullest. Now in the next video, have Flammy day. Check out the main channel too. Ciao!